So good afternoon. Our first speaker this afternoon is going to be Tom Williams, WA1 MBA. I'm sure most of you know Tom. He's had quite a bit of experience in the upper microwave bands. Tom was first licensed as K1 URO back at age 14. I thought I was a young guy. And has worked for a number of companies in the Northeast, working in millimeter wave imaging and image understanding. He currently lives in Massachusetts and is consulting for a drone company in Kansas. That's cool. He's done an awful lot of things in the EHF spectrum, and in the 90s achieved the first QSOs on the 145 and 120 gigahertz bands. He's part of the Northeast Weak Signal Group and has had the pleasure of creating and administering the microwave email reflector that I think we probably all are part of. Built a number of 78 gigahertz LNAs for the amateur community. He has a number of technical publications and 6 patents. If you please welcome Tom Williams, WA1 MBA.
Thanks, Dave. Let's see if I can get my act together here. I usually don't and can't. I know, iced tea, that's the thing. And of course I have to learn a new button box for the movement of slides. There we go. Okay, now I have to get my slides up. Now that's going to be interesting. You know how to do this? You're the man. I changed my slide set a bunch of times, and Al asked me for my slides if he could give them to him back in September, and I said, well, I will, but you know how things change. And I said, yeah, I tend to change things at the last minute, and this time I didn't. They look pretty good. So that's hopefully, there we go. What's the next step? There we go. Okay, perfect. Thank you. Okay, so I want a raise of hands. How many people know, not think, believe, dream, know that they were at Microwave Update 1999, 20 years ago? 1, 2, 3, 4, 5. Okay, how many think maybe they were and not too sure, but probably? There's a lot more, okay. And how many absolutely know that they weren't there? Excellent, good. So I'm not preaching to people I've preached to before, at least on this topic. Now there's one other thing. I also gave this same talk, or something very close to it, last spring at the Super VHF conference in the DC area. Were a bunch of you there? Yeah, so you guys have seen some of this before, if not all of it. All right, very good. So, ooh, that doesn't do it. Oh, there's an on button. I was warned about this. On. I see buttons to turn things on this side, but I don't see any lights coming on. You want to help me with that? Oh, that side. All right. Ta-da. This is not an EME. Okay. That's right. So I'm not going to talk about EME. I like talking about EME because I don't get on EME, but I'm not going to anyway. So I gave a talk back in '99. I relied on data from a program that was used primarily for the interaction between light and solutions, which is very useful when doing scattering devices that use lasers to find like how much fat is in milk and things like that. And I made some mistakes in its application, or at least the guy that helped me didn't know about the mistakes. And so I got some stuff wrong. Basically, the dielectric properties of water at RF change over frequency quite a bit, and they're not the same as they are at visual wavelengths, so that changes stuff. Also, there's some new bands. And believe it or not, nature itself has changed. Now, people don't realize this, that nature itself changes. Well, the thing is, we learn things about nature we didn't know before. For instance, For instance, people who are engineers realize that there's no such thing as an absolutely pure, perfect square wave. That's true. There is no such thing as a perfect square wave. In fact, they'll go on to say there's no such thing as a square wave in nature. Well, there are. This is an actual picture. It isn't photoshopped. But what this is really is boats going in two directions and waves coming in orthogonally when they hit the shore. My talk, what is it about? First thing I'm going to talk about what scattering is, then I'm going to talk a bit about what rain is, and then how does scattering work? And it depends on a lot of stuff like the particle size, dielectric values, wavelength, and then there's angles and polarization effects. And then I'll talk a little bit about rain scattering possibilities at bands above 10 gigahertz where we typically do it. So scattering means throwing things around different directions. Technically, things go in directions often not in the direction to which they were sent. So we say things like scattered to the four winds. And that's the same word. It's meant to mean the same thing that we're talking about. Tom's scattered new phone delivery. What does that mean? I'll get back to it. The Irish are scattered around the globe. The S11 scattering parameter value is minus 7 dB. Okay, and there's probably some angle associated with that as well, right? So hams are really interested in the interaction between TEM waves, transverse electromagnetic waves, the stuff that goes through the air and through coax. Not, by the way, the stuff that goes through waveguide, but that doesn't matter. Knife edge scattering, for instance, tropo scattering and rain scattering. I won't talk much about the other two. I will talk mostly about rain. But first, a year ago, almost to the day, October 5th, a year ago tomorrow, I ordered a new phone. I buy each Pixel phone from Google when it comes out. So I ordered this phone. I was waiting for this phone. And it was going to be delivered to me in Massachusetts from California. And it was sent via FedEx Ground, and I was sent tracking information. FedEx Ground, not FedEx as we know it. FedEx Ground, there is a difference. So it was scheduled to be delivered on the 20th, just a few weeks after I ordered it. And this is the first path it took. Hold on. It got to the middle of Connecticut, okay? 60 miles from my house. And then what did it do? These are all the points that it stopped along the way. Every hub it hit that it was checked in and out of. And then what did it do? It arrived. It arrived. Only going through 17 states. A buddy of mine used to work for Union Pacific, and when I told him about this and showed him this, he said, "Boy, those look familiar. Can you tell me what towns those are?" And I did. He said, "Every one of those is a railroad depot. It went by rail." I don't know what happened when the first time it came to Connecticut. Apparently there was no rail from Hartford to Amherst. So it arrived on November 5th. Just 1 month after I ordered it. Now, I could have got there faster if I used these guys. This is purported to be an actual advertisement. I don't know if that's true, but the Pony Express was, in fact, hiring people in St. Joe, Missouri, which is just north of Kansas City. Young, skinny, wiry fellows, not over 18, must be expert riders willing to risk death daily, orphans preferred. I don't think I'd take that job. Okay, examples of scattering. Well, even on a beautiful sunny day, this blue sky, it turns out the sky is blue because of scattering. On nice sunsets, there's a beautiful red sky, that's scattering. And there are radio signals that pass through media and they scatter. So, I just talked about the atmosphere and visible light, and scattering increases with frequency to a point, so the sky appears to be blue. Violet is absorbed more, so you usually see the violet in the illumination of the sky, but you certainly see the blue. The atmosphere in VHF. How do we get scattering at VHF in the atmosphere? Well, it's due to turbulence. And what is turbulence? It's the movement of air. And when air moves, how does it do that? All by itself? No. There's some place of lower pressure and some place of higher pressure, and because of the differences in pressure, the stuff moves. And then those cause vortices, which move even more, and then there's heating from the sun, the cooling from the earth, blah, 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 and then cooling in the upper atmosphere. You get these turbulences that are constantly flowing. And you tend to get boluses of air of different dielectric constants than other boluses of air. And the range of those sizes of boluses are a few meters to dozens of meters. And those act like big balloons of different dielectric constant, very slightly different, which is enough to actually scatter VHF. This is how it was explained to me, but I accept it. So you'll have to accept what I say. Anyway, but this talk is about 10 to 300 gigahertz scattering, so I'm not going to talk anymore about this kind of VHF scattering. As we know, you've got a scattering medium, you've got two antennas, they both can see the medium, and there's some communication that can take place through the use of that medium as a scattering. There's something called knife edge, where there's a transmitter, let's say for the moment, is transmitting this direction, and the wave goes along, and then there's no more place for it to go down here. Keeps on going up there, but somehow there's energy that pops off the other edge. There's actually beams that are formed down there, and this is very similar to what's called a slit experiment with light. And there's ways to calculate, based on the frequency and the distance and whatever, what the general idea of how much signal you get the other side. Sometimes it's pretty strong, and I've done this before. I think many of us have. And then there's rain scattering, where the medium is rain. And some of us have done rain scattering on 10 gigahertz, and some at other frequencies as well. So that's what I'm going to be talking about. First, what is rain? What is rain? It can be beautiful stuff, it can be difficult stuff, but it's the stuff that comes out of the air. Why do we call it meteorology? Meteors are things that come out of the air, come from the sky. So meteorology is the study of things coming from the sky, although most meteorologists don't know very much about meteor showers. They know more about rain showers. They often will report meteor showers on their forecasts. Barry, are you here? Where's Barry? There he is, right in front of me. Do you ever watch the Channel 10, Fox 10 news on TV in Arizona? No? Good for you. I wouldn't either. This is why. I don't understand what the temperature of 2,385 degrees would do for me. That would be a warm day. And this guy is just talking along, you know. It's 66 here and 64 in Scottsdale and 2,385 up in Wickenburg. That's right. So particle sizes. This is a combination of the way water molecules actually glom together and the way humans describe stuff. So I can't say absolutely for sure that there's this range between 100 nanometers and 1 micron where you don't find raindrops in the atmosphere, water drops in the atmosphere. I can't say that for sure, but there certainly appears to be that case. So H2O water vapor is just individual molecules of water that are in the air, like in this room. There's plenty of them. They're bouncing around having a good time, taking up space. Haze is between a few dozen water molecules and a few million water molecules getting together and forming big enough things that you could actually see the particles if they were in front of you. But haze often is not visible up close. And it takes a large volume of it before you can actually see the haze. And it has interesting properties just like any scattering medium, and it has some interesting properties at visual wavelengths as well. And I might mention those later. Clouds, rain clouds, fog, they all fall in this general range here. Mostly well above 1 micron diameters up to the area where you start actually getting rain and drizzle, 100 microns plus. And then rain, I just drew a bunch of different distributions in there of things like drizzle, light rain, and tropical downpours. When things are actually falling from the sky, which isn't a cloud, it's rain. It's a meteorological event. You know, they tend to be in these sizes here because they're big enough to have gravity act on them more strongly than turbulence and just Brownian motion pushing them around. And they fall out, and that's the stuff that comes out of rain clouds and that we call rain. So I drew up there 3 different types of distributions of rain in what we call drizzle, light rain, and tropical downpours. But you can often get a combination of all those 3 at the same time. They're not really exclusive. So why do raindrops only get so big? Well, first of all, raindrops are not shaped like that. People often think they are. That's the way you draw them in cartoons or whatever, but that ain't the way they're shaped. They're shaped like this. They're pretty much spheres. And it's because their tension, the tension of the surface is strong, and the air flowing around them is pretty minimal in terms of being able to lift them, and they just stay as spheres. As more and more particles get together, they get bigger. And eventually they get so big that the bottom starts to flatten from air resistance. And then eventually, a little bit bigger, and a knife edge sort of appears in the middle, a dimple, and they pull apart, and you're back to 2 spheres again. So there are some of these floating around in heavy rainstorms, these different shapes, but they're transient. So most of what you see is in a certain range, and it doesn't really you don't get a lot of rain bigger than about 3 millimeters. And that's, what's that, 1/8 of an inch. There is some bigger, but not much. It tends not to last very long. I did mention something about the having the dielectric constant wrong, and dielectric constant figures big into scattering properties. So there's 2 portions of a dielectric measurement. There's E prime and E double prime, and over the range of, which I wrote it down here, 10 to about 250 gigahertz, they do change quite dramatically. You tend to use the square root of these in most equations, so these numbers are pretty big. But the fact that they change dramatically means that the speed that a wave travels inside a particle of water changes depending on the frequency that you're operating at. So they look bigger or smaller to the wave that's hitting them. So, how does scattering work? I don't know if I can really explain this. I don't know if we really ever have. I only learned it myself 20 years ago, and even then I wasn't sure, but I'll give it a try. So here we go. If you have a slab that is a block of material shaped like a slab, like your telephone, for instance, but it was a consistent, homogeneous material, and let's say some kind of a plastic or some kind of a dielectric, not metal, then when a wave comes in and hits that material, then depending on the angle and the difference in dielectric constant between, in this case, air and the plastic or whatever, you get some sort of split of that wave into a reflected component and an internal component. And like I say, it depends on all these different factors: the angle, the material in, the material out, and actually the polarization as well. And the internal one then will do the same thing. It'll hit this boundary and it will say, oops, there's a boundary condition here. I've got an internal reflection and then an external reflection. So the external is actually an emission, and then there's another internal reflection and da-da-da-da-da-da-da forever, but of course not. And you can write an equation and it comes to a simple number in the end. But that's basically what's going on inside the slab when a wave hits it. So I've got a big slab of material sitting in the room, and I got 10 gigahertz, and I got a nice beam, and I point it at a certain angle, and I go over here and I start measuring what kinds of energy I get at different directions, and it follows these properties very precisely. What goes on in a particle? Well, all those things go on. There's reflection off the front surface. There's refraction inside, okay, which comes out. And there's some internal stuff that goes on. Particles tend to be pretty small relative to the wavelength, so that internal stuff is guided by some principles that are not the same as we just saw in the slab, because the slab was meant to be fairly large relative to a wavelength. The other thing that goes on when the wave enters the object is that it excites it. So it has an exciting time, 10 gigahertz does, when it hits the rain. And the rain says, oh goody, I'm going to absorb this energy. It looks like absorb, although I'm not going to actually absorb it. I'm going to let it bounce around inside me and emit it in all kinds of directions, in all kinds of ways. So it looks like cavity mode excitation. So it's a very small cavity and it's being excited and it's emitting the energy. It does absorb a little bit of it because it does have an extinction quality, a way of actually absorbing the energy, and it warms it up. But that takes a lot of juice to actually warm it up enough to measure. It's mostly pretty transparent. And we know that cavity modes are interesting. You can have all kinds of many modes excited if the wavelength is small relative to the cavity itself. And not every piece of matter that you're going to be bouncing your energy off of or scattering it from is circular, but I'm not going to go into that. In every case you get reflection, refraction, and this emission, this absorption and emission. There's several formulas that the early folks who did work in this area, primarily with light, applied in order to get some kind of a reasonable result in explaining what goes on when light hits things like rain and other particles. Rayleigh was one of the first dudes, and he came up with this expression which raises it the frequency to the fourth power that says as the medium is excited, where all the particles in the medium are the same size and distributed so they don't touch each other, and there's lots of assumptions here, then a wave, as the frequency doubles, the scattering goes up as 2 to the fourth, okay, which is 16, right? So if you just double the frequency from something to something, then you should get 16 times more scattering going on, more of the effects of scattering, and that's good. But that turns out that equation kind of stops at some point, at some ratio of the wavelength to the size of the sphere, and it takes on a new direction, which ends up with this thing here, which that goes off to infinity. But after it gets after these waves and amplitude versus frequency get too close together, it looks like a straight line. So the guy that did that work, his name is Me, and so we now have the Rayleigh, Me, and optical regions of the wavelength to size ratio determining how much energy is going to come out, is going to be scattered, and how much is going to be ignored, consequently. So knowing that f to the fourth thing, and assuming everything else is the same, which it isn't, that if I had some kind of a scattering going on, where I had, let's say, 10 dB of signal-to-noise ratio over a path using a scattering medium, and the scattering medium stays the same, you know, you're just going to hold the world sort of stationary for a bit. I had 10 dB signal-to-noise ratio at 10 gigahertz, I would have 20 dB at 10, I'd have 10 dB at 5 gigs. I'd have 1 dB of signal-to-noise ratio at 3 gigs. I'd be below the noise at 2 gigs and way below at 1296. I personally have heard scattering from 2304 to 24 gigs. I've never heard 2304, but below 2304, but I have had reports from other people who said they have heard it at 1296. So, but it gets weaker and weaker and weaker as you go down in frequency. It gets stronger and stronger as you go up to in frequency to a certain point. So now we've got this situation where we've got two storms, storm 1 and storm 2. We've got two stations, A and B. A and B can't communicate because we've got these intervening obstructions, these mountains. But there's a couple of storms out there. Turns out that there's an effect of preservation of polarization that matters when you're looking at situations like this. So Don, if you could come up. It's going to take me a second to get my materials together. Most talks don't need tubes like this. Because most talks don't have arrows. Okay, I'm the transmitter. Okay? I'm going to send a horizontally polarized, this is the E field, toward the scattering medium. So if you'll orient your arrow so it's the same, there we go. All right. So now I'm transmitting, and now it looks like this scattering medium is retransmitting with the same polarization. Okay. People over here see the tip of my arrow. It's like working me off the side of a dipole. How good is that going to go? That's the null. You're not going to hear me at all. People over here who try my scattering volume are going to have the same problem. If this angle is 90 degrees, and I'm using horizontal polarization, poor signals. Poor signals. If the angle is a different angle from that, like 30 degrees, back over to there, that person is going to work me fine off of that. Or somebody over in that direction. They're going to see this with their horizontal polarization and work me just dandy. In fact, the apple is approximately the shape of the beam. All right? Let's move to vertical. Okay. Now what? Everybody sees that with their vertical polarization. Everybody in the room, that's perfectly good. You're aiming at it, you're getting 100%. No prob. So if you want to work scattering, you should use vertical. Do we use vertical on 10 gigs? No. Years and years ago we used to. Back in the wideband days, many people used vertical. And they did scattering with those crappy signal-to-noise ratios and their lousy transmitters. They did scattering. They had vertical polarization. They also had another advantage, which I'll tell you about in a moment. Thanks, Don. Yep, a hand for Don. Thank you. So, there's another thing that happens with rain scattering, and that's that rain is sitting in turbulence. You really can't have rain unless there's some kind of air movement. Some types of rain are very gentle and there's very little air movement, but many storms have lots of air movement. And so the rain is going in some direction, generally because the storm is moving in some direction, and sometimes is moving in multiple directions simultaneously because there's turbulence and circular motions and convection and whatever going on. So what happens to your signal when it hits that kind of a medium? Well, the medium is moving away and toward both stations. Well, that causes Doppler shift. How much Doppler shift at 10 gigahertz? Quite a bit. You know, if it's only 30 miles an hour, it's good enough for a radar gun running at 10 gigs to give you an accurate reading. So this is an equation. I don't suggest that you memorize it, read it, or think about it. But modulation that depends on coherence of frequency will lose intelligibility. So if you're using CW and you're listening for a tone, you might get or depending on the severity of the Doppler shift. And single sideband, which might be, we're hearing you fine, turns in, fine. And the other guy says, what? And I say, I hear you fine. And the other fellow says, what? But what happens when you switch, so CW and sideband stink. It's like strong aurora. Now, sometimes the storm is really just moving in one direction, it works fine. no problem. You just tune it a little differently. It's like a RIT. You turn your RIT on and you just change your frequency. But FM, what happens to FM when you take and you shift its frequency in different directions rapidly? What happens to FM? It has noise on it. It just sounds like noise. You hear the voice and you hear some noise on it. It's remarkable. You can't hear the station at all on sideband. CW is hard to copy, and the voice comes through with fidelity on FM. It just requires that you could put up with some noise. But it's just noise, because the frequency modulation that's going on in the Doppler shifting turns into amplitude modulation in the received demodulation, and bingo, you just got noise. So this works beautifully. Quite often I have been in Rainscatter contacts and tried FM and things that work beautifully for using voice. Horizontal polarization will experience serious nulls at 90 degrees. I've already gone through that. So the conclusion might be that if it's available, try vertical polarization. It might not be available. It's really hard to move most of these dishes into a different polarization. Okay. So I'm going to talk for a moment about SHF and EHF. That is, what about the higher frequencies above 10 gigahertz? Is it possible to do Rainscatter up there? Most of us barely have enough power to even make a QSO, let alone use Rainscatter to increase the distance of our QSOs. So it might be just a little silly to be talking about this, but someday we might have some power. I mean, there are 6 and 10 watt amplifiers available for 47 gigs. And there will be eventually, you can buy 1 watt amplifiers for 78, although you can't use them in this country. So let's talk a little bit about that. So this is a plot. You know what a beam pattern looks like for a Yagi, for instance, or a beam pattern for a dipole. This is a plot for 10 gigahertz, and the illumination comes in this way. So this would be horizontal, and this would be vertical. Coming out of the paper would be a vertical antenna. Okay, the energy coming in. So that's the illumination direction. And if we had very heavy rain, we had basically only 3 millimeter rain, then the vertical and horizontal will be pretty similar looking. They'd be these round things with a little bit of a squish, a little bit of a dimple in the horizontal one. And if we had 1.5 millimeter rain, which is pretty heavy rain, it's not tropical downpour, but it's pretty heavy rain, it would look like this. Things reverse a little bit, but it looks like this. And if we have drizzle, then it looks like this, and this is a dipole. See, the dipole's right here for horizontal, right? You don't see 90 degrees, you don't see 90 degrees, because that gray, which you can barely see probably on the screen. But if you have vertical polarization, it's the circle. It's 100% all the way around. So I've done the same thing, put them all 3 on the same from this size, from this frequency up, because it was possible. It wasn't possible on 10 gigahertz to do that. But just a matter of the graphing thing. And you can see that at the smaller drop size at 24, you still got that donut, that nice bagel sitting there. And at the larger drop size, you're really getting more scattering going on, but it's got very little shape to it at all. It's pretty much in all directions. 47, same idea. Now the larger drop sizes are starting to show a little bit more structure, like right here. And at 76 gigahertz, even more structure at the larger drop sizes, but the small drop sizes still appear to have that same bagel donut shape. So if it's light rain, it's going to have all the same properties as you do at 10 gigahertz, well, except for various losses, which I'll talk about later. And but the large drops are starting to get a lot of structure in them. If you look at this dark green one right here, see that one? All right, what's that starting to look like? Looks like about a, I don't know, about a 7 dB gain, a 3-element Yagi, something like that. So it's starting to get some forward gain and some side lobes. Anybody have a 100 watt 122 gigahertz amplifier available? I'll buy it. They actually are made, but only for companies with millions of dollars. So here we get a lot more structure, a lot more ripples. What's causing all this extra structure at these larger drop sizes? Well, you're running higher modes in that cavity, which is the raindrop. And if you have higher modes, you have more waves in there, which can interact in different and interesting ways. And they start to add up more in one direction, which is the direction of propagation. So it starts to look like a Yagi. It starts to look like a multi-element Yagi in some ways. Not exactly, but that's a pretty good analogy. But again, what we're starting to see at 122 gigs, that this donut is starting to open up a bit. And there we are at 134 gigs, and at 241 gigs, where every size of raindrop starts to look a little bit like a Yagi. Extinction. I did mention a couple times that I was going to talk about the fact that there's a loss of energy at the higher frequencies than there is. There's two things that cause it. One is scattering extinction. The scattering process itself causes more energy to be lost. There's actually three things. A second thing is the raindrops themselves internally have more absorption of energy and conversion into heat. And the third thing is that rain is in moist air. And as we know, those of us who work on EHF bands, the more humidity, the higher the dew point, the more moisture there is in the air, the more absorption there's going to be, because it's a bipolar molecule sitting out there and just pulling energy out to help it spin. So there are a number of things which cause the extinction of the energy in a volume, a realistic scattering volume. So they've come up with these equations. I don't like those things. But I talked to my buddy who does this for a living, and he said, you know what we use? F to the 1.9. You know what we really use? F squared. So there's a very simple rule of thumb to know what the extinction is. The extinction goes up by approximately the square of the frequency. That doesn't include the moisture in the air, but it's the extinction of due to just the rain. This is a rain number, F2, F squared. But you can plot what it is, and these are actual plots of real numbers. It's in your proceeding. If you're in a light drizzle, then at 100 gigahertz, you might have 0.5 dB per kilometer of extinction. Not the atmosphere, extinction due to the rain. And if you're at 120 gigahertz or so, which is about as far as this thing goes, then and you're in a tropical downpour, you'll be losing 25, 10, 20, 30 dB per kilometer, which is just makes it impossible. So you can't really, at that frequency in a heavy downpour, you really can't use rain scattering. I mean, it'd be just crazy. You might get something backscattering that will look pretty good, but if you're going through even 1 kilometer of rain, which is a pretty small cell, you'd lose it completely. But at lower frequencies, it's not too bad. This is why 10 gigahertz works really well, right? Even a moderate amount of rain, 10 gigahertz, where you get lots of scattering, you're only losing 0.2 dB per kilometer. And if a storm's 3-4 kilometers across, no sweat ski. It's in the EHF regions that we start to see some big numbers. So I made a table based on 1 kilometer and a temperature of about 60 degrees in the atmosphere and about 50% relative humidity in the storm. Now those are just numbers, but this would be like a 4-dimensional graph if I tried to put too much into it. So I had to make some assumptions. And here you've got the bands, okay, and the rain rates, millimeters per hour rain rate, which is different from the size of the raindrop. And anything above about here is, you know, this is 1 inch an hour. That's a pretty good storm. 2 inches an hour is, you know, you're in a hurricane, you're not doing much ham radio. So there you go. That's the revision of an old talk to some of the same people and many new ones. There are some references if you're interested in reading, and those are even references if you're not interested in reading. I always like to offer some professional tips to people. I found this really works well. A little coconut oil speeds up the whole process. I recently moved to Cape Cod just a couple of months ago, and well, I was there on Christmas before we moved. We owned the house, and so we were slowly getting the house ready to move into, and then it was Christmas, and we didn't really have presents for each other, so we drove down to Rock Harbor, which is in the town we live in, and we were pleased to see this. It's one of the most magnificent sunsets I think I've ever seen, and they're not that uncommon. But thanks to scattering, we can enjoy this fantastic scene. So, any questions?